Hi! In this video, we'll be going through now on a systems of first order linear equations. So we already went through previously what happens when we have one first order equation and what happens if we have a second order linear equation. Now we throw away the second order and we think about it as a system of first order linear equations. So we'll take a look at examples to actually visualize what do I mean. So firstly, what is a system of equations? It's like x plus y equals to 1, then x plus y plus z equals to 2, then z equals to 3. Then this can be a system where you solve for x, y, and z. So if we have a first order differential equation will be you have a derivative on this side and the other side don't have a derivative at all. Then x2 prime will be this. So you just define it in this form, and if this function is linear, meaning the x1s is the x terms have no square or anything, then the system is said to be linear. Otherwise, it's non-linear. And higher order differential equations can be similarly defined in this manner. And what's so important about it is equations of higher order can always be transformed to first order equations. For example, you have this second order differential equation. What you do is you just let y equals to x equals to u prime. Then, okay, so the first one is just x1 is u, so x1 is this, u, so x1 equals to u, x2 equals to u prime. Then you can write this equation now as x2 prime plus 0.25 x2 plus x1, or you can actually just write it in this as x1 prime, but you want to have only one prime on one side, so you cannot have that, so you need to write it in this form. And then how do we want to do it now is, now we can do it for any nth order equation. And so if we have y to the power n derivative, then we just define what's y n minus 1, y n minus 2, and so on. And we just let that be the different x's, and then x1 prime will equal to x2 and so on. So you can actually see how you can convert a higher order differential equation into a system of linear equations, first order linear equations, which is very useful now because they are first order equations, which we have a lot of techniques to solving it. So what is linear versus non-linear? Again, we just said that this function in terms of all the x's is a linear function, so it's just a linear combination of these terms, but t can take on any value. So, and if this portion don't have any t inside this function f, then the system will be autonomous. And if every fi is a linear function of the x's, then that is the x1 prime equals to this form. Then we say that the ODE is linear. And if this g's, that means the t, there's no function of t only, then we say that the system is homogeneous, like how we define it very similarly for first order cases. So the reason why we went through so much first order is so that this portion can be built upon easily. And the good thing about writing it in system of equations is that you can convert it to a matrix form, and we can use linear algebra to help us solve many problems now because it is in matrix. We can define it as a matrix. So we have our x1s and x2s all the way to xn's derivatives, and so we can put a big derivative sign of, we just differentiate the vector, so it's a vector calculus in a sense. And then our coefficients from the system of equations will form this matrix, n by n matrix. So with that being said, then this is the coefficient matrix, and then the x1 to xn are the variables, and then the gt will be all the terms that are just t will be put to one side, and that will be just like the column, like the functions in terms of t only. So if this part is zero, then it is homogeneous. If not, it is not homogeneous. So like our first order case, we now have the theorem that we consider the initial value problem of this thing. And we consider the initial value problem and assume that the components p and g are continuous functions of t. Then there will exist a unique solution to this initial value problem. So the proof of this is just an extension of what we have went through in the first order, in the one equation case, so we won't go through it again. But for the superposition principle, it's very easy to see, and you now see why there's so much similarities. Because once you write it in this matrix form, you just manipulate as like a linear combination and you'll be able to solve it. So you just plug this equation into the system and just check that it's a solution. And because the derivative is a linear operator, then it works out. So now the question is, can every solution be written as some linear combination of two? Then if it was true, then we just call it the fundamental set of solutions, and the general solution will be just the linear combination of x1 and x2. So this is equivalent to the saying whether the x1 and x2 can span the whole of R2. So let's just start with defining the Wronskian again. So if the x1 to xn are n solutions to the homogeneous equation with n variables, then we can define the Wronskian as the determinant of these solutions. Now you write it as column vectors. And just like a second order equation, so with the second order equation, the Wronskian non-zero will imply that the solution form a fundamental set of solution. The proof, again similar, we'll just show it to show the similarities. Now we just take this to be the non-singular case, and so there will be existing a vector such that this holds, and with that we can expand out this to get this linear combination, then equals to b, which equals to xt0, and by the existence of the unique solution, this linear combination must be the only solution and hence must equal to xt for all the t's. So an example is like when your x1 is this function and your x2 is this function, and you want to form the fundamental set of solutions for x prime. Then first you just check whether the Wronskian is non-zero. If it is, then this do form a fundamental set of solutions. So you can see a lot of similarities between the first order case and when you have system of first order equations. And now we move on again. There's also Abel's theorem, and similarly it states the same thing but now in a more general sense with multiple variables, and is that this Wronskian is either always zero or never zero. And the proof of it is almost the same. You rewrite it in a form such that you can do variable separable on it, and actually show that it is the exponential integral of the coefficients, and you'll be done. So the last part of it is just an extra fun fact, and that will be just if you have this solution and the solution there is a complex valued solution to the equation, then the real and imaginary parts will also be a solution. And the proof of it is, well, we substitute this complex valued solution into here, and we actually see this following thing. Since we know that the assumption that this px is real means we can separate into the real and imaginary parts like this, and a complex number is only 0 if and only if the real part and the imaginary part is both 0. So we can conclude that this is 0 and this is 0, which actually is, you just need u prime t equals to pu, which just is this system. So it actually shows that the u's and v's are also going to be solution. So that's all for this video. I hope you have enjoyed it. Feel free to like, share and subscribe, and I'll catch you in the next one where we continue now into more studying solution sets for system of linear equations. Bye.